My name is Daniel James. I'm a professor at U of T up the road. I've been there for about 5 years. Before that, I was at a place called Los Alamos National Laboratory in New Mexico, which is a place where they do rather sinister stuff some of the time. They do nice stuff some of the time as well. And to tell you why quantum, what it is, well, I don't really know what quantum is, but why you should care, I might be able to do that, or why I care anyway. I went there 15 years ago, 1995, as an optical engineer. I wanted to solve the world's energy crisis. I wanted to figure out how to make laser fusion work. How to make it work, sorry, we don't know how it really works yet. And I was very good at doing things like what Krister demonstrated, doing these completely deterministic, completely non-random predictions of what's going to happen next when you shoot a big, fat, powerful laser beam at some sort of nonlinear crystal, and you see what comes out the other side, and then we could feed that into some sort of little pellet and make it go bang, and we got ourselves a fusion reactor, and the world will descend into broad sunlit uplands of energy independence and all that stuff. Unfortunately, it hasn't worked yet, but that's another story. Anyway, in 1995, working there, one of the problems with working there is you have to do what you're told. And all of a sudden, well, just as I started getting my teeth in that problem, certain gentlemen in dark suits and dark glasses from a United States government agency, which I'm not allowed to say, certain letters which, if you found out what they mean, they changed them so that you never do actually know what they mean. They suddenly came and said, no, you're going to start working on these things called quantum computers, which was somewhat perplexing because I didn't know what it was. I wasn't really all that up into quantum mechanics. So what is the difference between quantum mechanics and the sort of classical mechanics which Krister was demonstrating? This is the thing about if you can see it's coming and you can predict it. You know what the situation of this glove is. It's flying through the air. You can know its position. You can know its momentum, and you can write down equations and solve those equations and figure out where it's going to land. I mean, we can do that in the head. Max, he did it in his head. Clever guy, solving differential equations. And he was able to catch it. And that's what you do. That's what theoretical physics is to a very large extent. This is all invented by Newton and Galileo and all those Herberts way back when, how to do this mathematics. But as I said, 100 years ago, there was this revolution where they found that at the very basic level, the universe doesn't actually behave like this. There's a sort of dichotomy there's a sort of divorce between the things that you can measure about something and its actual situation, its actual state. And that's what quantum mechanics is. You cannot actually predict things. All you can do is predict the probabilities of what's going to happen. And fundamentally, in the quantum mechanical level, if you had a quantum mechanical glove flying through the air, it could be doing lots of different things. But only it's probably going to end up in Matt's hand. It's only might just end up doing something completely unexpected. But and at the real microscopic level, those different probabilities of things which might happen become much and much more realistic. How can you use that to build a better computer? Well, let's say you want to solve a mathematical problem. Like, for example, I give you the number 15. You want to know what the numbers multiplied together to give you that are. It's called factoring. So 3 times 5 is 15. I went to one of these old-fashioned schools in Britain where you'd have to recite it, and if you weren't shouting it loud enough, they'd hit you. So I know 15 is 5 times 3. Don't get me started in the education system. But how does the quantum computer help you do that? If you're actually solving something maybe a bit more difficult, like, for example, this is 338 Queen Street West. If you want to know what the factors of 338 were, what you do is go through, does it divide by 2? Does it divide by 3? Does it divide by 4? And so on. You keep trying different numbers and trying the long division and figuring out how to do it. You have to do it over and over and over again. And that's a repetitive process. You can do it, you can get the answer eventually, but it's going to take a long time. But a quantum computer, it sort of takes advantage of this difference between classical and quantum physics, in that in quantum physics you can be more than one thing at a time. You can the glove can be taking multiple different paths as it flies through the air, and only one becomes very much more probable than all the others. But in the quantum mechanical level, it could actually have two different paths. People are doing experiments where they can send, well, not gloves, but say carbon-60 molecules, really large-scale things, and they can have it going on two different paths at once, and they can see the effects of it going through those two different paths at once. These large particles are in fact quantum mechanical. So there's these multiple possibilities. And if you can harness this, you can set up a computer which can have all possible numbers dividing the number that you want to factor all at once. And you can just sort of down-select the answer that you want. So you can replace a whole series of difficult, repetitive, long division sums by just one, like that. Makes it very much faster. Now, what are these guys in dark suits and dark glasses interested in this for? Well, it turns out there is a type of code which is based on factoring. It's called a public key encryption system, or RSA encoding. And if you can find the factors of large numbers very quickly, you can break this code. And there are sort of these spook agencies that do this all full time. And this quantum computer was invented, the idea of doing this was invented in 1994, and an actual design by where we could implement it using trapped atoms, trapped ions in a specific sort of trap was also invented just the same year. Now, unfortunately, the experiments to make these quantum computers work, you need a room about as big as this, filled with the best lasers in the world, sort of lasers that people win the Nobel Prize for inventing. In fact, the ion trap experiment, I think is the product of about 5 or 6 different Nobel Prize winners, all of whom are still alive. So it's not like it's ancient, easy technology by any means. So it's not a device which is going to be something you can buy anytime soon, but we're making small steps, that's the thing. And these steps are continuing. We've done things like, besides doing very simple factoring experiments, factoring algorithms like factoring 15, we know what the answer is. We've also done something called quantum teleportation, which is kind of a spooky sounding thing, but that essentially says, here's one atom. What makes one atom different from another atom? Well, it's this quantum mechanical state, this underlying description of the actual situation of that atom from which we can predict the probabilities of different outcomes occurring. And that's the most fundamental idea of what makes one atom different from another. What makes you, we're all essentially large sacks filled with carbon, oxygen, and hydrogen, and a few other things. We're all a bunch of atoms. But what makes me different from you? It's the individual states of all those different atoms. And how can I change the state of one of my atoms how can I swap it with the state of one of yours, for example? Well, that's a process called teleportation. We can exploit this entanglement that Yasaman was talking about in order to essentially swap, like a shell game, the state from one to the other. And that's been realized. This was done in 2004, 6 years ago now, using these trapped ions. And we're making progress. We're building bigger and bigger numbers of entangled states in the different technologies. It's getting there. It's not going to be a marketable quantum computer anytime soon, but the possibilities that these present, I like to think of it as 100 years ago, domestic life was a whole bunch more difficult than it was now. You had to do, for example, you had to have a whole day every week allocated just to do the washing. Now we've got electric washing machines who can do it in half an hour. So the advent of machines, of electric motors and universal powers made everyday life so much more easy. But can the advent of massively parallel computing make our life similarly very much easy? Can we remove the humdrum need for simple decisions that occupy so much of a life? How do you drive to work? What route do you take when you drive to work in the morning? That could maybe be solved by some computer working in some big place somewhere, and they tell you what's the best route to get to work every morning, and they're telling that for everybody coming into Toronto. And that would make everybody's life a lot easier because you get there faster. Just things like that. That large-scale, massive computing could revolutionize everyday life just as the advent of machines has revolutionized everybody's life in the last 100 years. So that's why I care. As I said, I don't really know what it is. We just are one of the people who do the driving, but we have got some nice places to